So hello, everyone. Welcome back. I will just quickly remind you that we have to wear masks in the seminar rooms. Thank you. Okay, today we have Sibylle, and she's going to tell us about cutting surfaces and recollements of dental algebras.
Yeah.
Take it away.
Thank you very much. What can I say? Second to last week, what a pity, but at least I think so. I've really enjoyed the time here, and I've enjoyed getting to know everyone very much. So this subject is very much inspired by cluster algebras in two ways. First of all, so how are surfaces related to dental algebras? That idea really comes out of the theory of cluster algebras, where somehow the cluster algebras of finite mutation types are associated to surfaces, and the corresponding quiver with potential has the triangulation of the surface as a model for its module category. And the other thing is that cutting surfaces in the context of cluster theory corresponds to Calabi-Yau reduction. And I want to show you what it corresponds to in the setup of dental algebras. So this is a joint work with Wen Chang from Shaanxi University and Haibo Jin from Cologne. Okay, so first let me introduce you how dental algebras and surfaces are related in general. Okay, so we start with S, a compact oriented surface. On that surface, we have a number of marked points. And these points are either in the boundary of the surface, or they can also be in the interior. Okay, and then we give ourselves a surface dissection. Into polygons, where each polygon is of a particular form, or one of two form of the form. Either it has exactly one boundary edge, or it has no boundary edge, and if it has no boundary edge, then it has an unmarked boundary component inside. So this is the data we start with. From this, we can define an algebra. So we call it a delta associated to that surface dissection. It's given by quiver and relation. And it's, of course, associated to this surface datum of SM and delta as follows. The vertices are in bijection with the edges of delta, and the arrows are from an arrow from a vertex I to vertex J, let's call it A, corresponds to, in the dissection, two consecutive edges IJ that follow each other in the clockwise order. So of course, everybody here knows this construction very well from cluster algebras, and then the ideal is generated by relations of length 2 that correspond in the surface to configurations like this, and then we have a relation, and then it's not surprising to anyone that the algebra A delta is a dental algebra. And if you don't know what a dental algebra is, then take this as a definition. Okay, and why can you do that? That's because of the following result, which we showed in a joint work with Sebastian Opper and Pierre-Guy Plamondon in 2018. And then a little later that year, Palu, Pilou, and Plamondon generalized it to the infinite dimensional case. So we showed it for finite dimensional algebras, because that's what we were considering. And they then included infinite dimensional ones. And what do we show? That the set of locally So this is this infinite dimensional part. Gentile algebras up to isomorphism are in bijection with surface dissections into polygons as above. So there are these two types of polygons. Either they have a boundary edge or an unmarked boundary component in the interior. And this is up to homomorphism. So there's a bijection. So the data of such a surface dissection is the same as the data of a Gentile algebra. Okay. No, I mean, it has to be this or this. So the question was, I do not allow polygons without boundary. And the answer is it has to either have a boundary edge or an unmarked boundary component in the middle. And that's simply because the dissection is the ribbon graph that generates the surface. And I don't glue boundary components into the faces because I don't want a closed surface. And therefore, every closed cycle in the ribbon graph will give rise to a boundary component in this way. Okay. Okay, then, okay. I have some remarks on this, some historic remarks maybe. Or okay, so in 2015, in a paper of mine, I constructed for a Gentile algebra. I guess at the time I was quite oblivious, maybe to a certain degree, to the cluster algebra story. So construct a ribbon graph. G, and in what way? So that the vertices of that ribbon graph are in one-to-one correspondence with basis elements of the two-sided circle of A, and of course the edges of the ribbon graph are in bijection with Q0. And then there's some ribbon graph structure, and with that, really the G and delta turn out to be the same thing. Okay, and then this was also considered by Coelho and Bauer in a paper that appeared this year, and they give a geometric model of the module category of a Gentile algebra. And this is based on earlier work by Coelho and Parsons on tiling algebra, so from 2017, so based on Coelho and Parsons from 2017, where they define these tiling algebras. And lastly, there's a graded version of all this by Likili and Polishchuk, which appeared in 2020, where they start with a graded Gentile algebra. And then what they get is a graded surface dissection, which is basically this surface dissection here with a grading. And I'll say something about this in a minute. But before I do this, let me tell you about the dual dissection. Which really plays an important role. Okay, I had some color. I want to always do this dual dissection in pink. Okay, and how is it constructed? So the vertices of this dual dissection, or you call them sort of red points, alternate. Oops, on the boundary with the marked points of our surface. And we also replace each unmarked boundary by a red marked point. Oop. Okay, so this obviously should be, I don't know if I can maintain that. Anyway, okay. And then what are the edges? Well, the edges of this dual graph are in bijection with the edges of delta. And we then get them by connecting red marked points such that each edge of delta is crossed exactly once. Okay, so they're given by such that each edge of delta is crossed exactly once. Okay, so I think probably an example is a good idea because they speak 1,000 words. Okay, here's an example. So we start with a surface dissection into polygons. So for example, we can take this and then we have to have this boundary component here. We number them 1, 2, 3, 4, 5, and 6. And then this gives us the quiver 1, 2, 3, 4, 1, 5, and 6. And then we have relations here. So an unmarked boundary component. Oh, well, I guess we can inscribe the arrows here like this. And then, of course, as the definition, we have the relations here. Okay, so this is an algebra of infinite global dimension. And then we have, but it's finite dimensional. And then we have the dual dissection. We alternate these. Can you see this pink well? Yeah, okay, good. We alternate the marked points on the boundary and put one here. And now there's a unique choice to connect two red marked points crossing each of the white edges once. Okay, excellent. So this is the dissection. And now, what is a graded surface dissection? Is simply associating a grading to each pair of consecutive edges. So associate, which is equivalent to associating an integer to every arrow of the algebra here. So this becomes then a graded algebra. And this is okay, so equivalent to when you have two consecutive edges here, I, j, you just associate some positive number, not positive, some integer to that thing. Okay, and why, okay, so what does this do for us? Well, luckily in Polychuk show that this grading is the same thing as the data of a line field on the surface. So they show that a grading of a delta determines, or simply of the ribbon graph or the surface dissection that determines a line field. Oops. Eta, which is a section of the projectivized tangent bundle on the surface. And what does the line field give us? Well, the line field allows us to calculate what is called the winding number of a curve, which is another integer that we associate to the curve, which comes by comparing the tangent space of the curve with the tangent space of the foliation of the line field at each point of the curve. Okay, as we travel along the curve. So every curve gamma on SM delta has a winding number W gamma, which is then some integer. Okay.
Sorry, Sibylle.
Yes.
Can you explain, please, how this line field is constructed?
Oh, I can tell you later. If I tell you how the line field is constructed now, then I guess I won't be doing much more in the talk. But I can tell you later. Yes. Okay. Okay, so from now on, yeah, I wasn't planning, but I can show you a combinatorial way on how to determine the winding numbers. And when you have the winding numbers for all closed curves on your surface or for a basis of closed curves, that determines the homotopy class of the line field. Yes, that's why it's a result. Lickety and Polichuk. But I can show you later after the talk. I'll show you by an example, and maybe during the talk I can also, when it's critical, there's a combinatorial way to see it, and I can say that. Okay, so from now on, assume that we have this graded Genta algebra associated to a surface dissection, and we consider it from now on. Consider a delta as a differential graded algebra simply with a zero differential. Okay, then extending some work by people to the DG case, namely the work of Beckett and Merklin. They give a classification of the indecomposable objects in the bounded derived category of ungraded Genta algebra. And well, this is one we don't generalize to the DG case, but we show that every object they have gives us an object in the derived category of the DG Genta algebra. But the paper of Arneson, Laking, and Puxtello, which gives a basis of the homomorphism space between two indecomposables, this can be generalized to the DG case. So this is from 2016. And then also a calculation of mapping cones in terms of that's called this classification here in a paper by Tonakshi, Puxtello, and myself from 2019, can also be generalized to the G case. And generalizing all that, I can tell you a sort of improved result of a paper of joint work. I mean, and this is still joint work by Sébastien Opper, Pierre Guy Plamondon, and myself. Namely, we show that this SM delta star, which is the dual graph, is a geometric model of the derived category of this DG Genta algebra with finite total cohomology. And it's given in the following way. We have the indecomposable objects in this derived category. And well, if we have zero grading, then they're in bijection with something that I will call graded curves, gamma f, and I'll say a little bit more about them in a minute, but let me just say that if the grading is different from 0, then we only have that all these graded curves give objects, and I think they're all the objects, but in order to classify them, a lot more work is needed, and at the moment nobody has done it. So if you like classifications, here's a job for you. Right, okay, so what are these graded curves? So gamma is a homotopy class of curves that either connect two white points on the boundary, or it connects a white and a red point, but really what it does, it sort of approaches it asymptotically like this, or it goes between two of these points. So it goes always in the anti-clockwise direction like this. Or again, so this is all possibilities for gamma, or gamma could be a closed curve, but then we only want to take those closed curves that in our grading have winding number 0, and we take all these curves together with a local system, which here is trivial, but here it gives us 1 parameter families, and somehow you have to think of these closed curves as the band objects in the derived category. Okay, so these are the objects, and in the 0 case, that's, we know by Beckett and Merklin that that is all that there is. And then we have a basis of the homomorphism space between two indecomposable objects which correspond to curves. So by slight abuse of notation, I will just write these indecomposable objects in this way. And this is in bijection. Okay, so maybe I should put it like this. It's in bijection with well-graded, directed intersections of the two curves gamma and delta. And how does that go? Maybe I want more. Okay, so I have that, and let me see which one is it. So here's gamma, here's delta, and here's our intersection point Q, and this Q might be on the boundary, it might be in the interior of the surface, or the curves can also intersect at a red marked point that is in the interior of the surface, so one of the unmarked boundary components. And then we look at the first crossing with this dual dissection delta star, and somehow if the grading agrees in a certain way, then we have a map. But each crossing does give rise to a map. There exists some grading such that this is a map. And yeah, okay, so I forgot to tell you about the F here, and this is okay, so what is F? F is what makes the curves graded, so it should have really come here. So let me make a little star and add it, because F is also what allows you to calculate the winding number. I was not going to give you the details, but I will try to say a little bit more, but I'm probably going to confuse left and right. So it might be plus or minus 1 or minus or plus 1. Okay, so F is a function from the set of intersections of the curve with that dual dissection. So remember, we have that red dissection that we built, and it is defined in the following way. Okay, let's see if I can do this. Okay, so we have our curve gamma, and then we have an intersection with the dual graph here. And if you look, then this dual graph also cuts the surface into polygons. And so I can always look how it traverses two polygons. And these polygons, these red polygons, are such that, I mean, I should sort of maybe do dot, 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 and dot, 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 dot. But eventually there will be a boundary component with a mark point here. Okay, and depending on whether this boundary component is left or right, you go up or down with your grading, okay? And I don't know what convention it is here. I would have to think about it for a long time, so maybe you can just check it later. So what is it? So here we start with f of x, just some integer, but then if the mark point is on the left, let's say then that f of y is equal to f of x plus 1, and f of z is equal to f of y minus 1, because the mark point is on the other side. And really, this really defines your winding number for the curve. Because, so we show this in a paper with Claire Mion and Pierre-Guy Plamondon, that this gives a combinatorial definition of the winding number of that line field that Likely and Polychuk define, and Likely and Polychuk basically also show this in a different way. I mean, not exactly like this, but one could say that it's equivalent. Okay, so this is the grading which gives us the winding number, and this is also the grading which somehow can be chosen here. So for every intersection point, you can choose a grading of the two curves such that you have a map. Okay, so finally, when we have a crossing of curves, we can resolve that crossing, and that also corresponds to an algebraic operation, namely to something else that is important in a triangulated category, and that's mapping cones. And the mapping cones of the basis maps of the homomorphisms are in one-to-one corresponding with the resolving of crossings, of the crossings. Okay, so what do I mean by that? So assume that we have a map from gamma f, some indecomposable, to delta g, another indecomposable object, and here we have that map phi. Then, of course, because it's a triangulated category, we have a mapping cone C phi. But what is that mapping cone? Well, that mapping cone, we can say exactly what it is. Namely, it's isomorphic to, well, actually quasi-isomorphic to alpha 1 f1 plus alpha 2 f2. So these are two objects in the derived category, which are obtained by resolving the crossing. So what do I mean? I mean, we follow gamma up to the intersection and then do gamma inverse. This is alpha 1, and then we do the other one, and this gives us alpha 2. Okay, so the mapping cones correspond to the resolution of the intersection defining the map. Of course, if the crossing is on the boundary, then one of them wouldn't be there, and we would have only one middle term. Okay, so maybe another example to see how that looks in practice. What do I do with the eraser? Ah, okay, thank you. Oh, I need to tie my shoelace. Okay, so for the example, I will do that in the zero graded case, simply because the grading is just adding a bunch of shifts, and I don't think it makes things necessarily more transparent. Okay. Now I know why it was over there. Okay, so what is the example? Okay, so I've chosen a very small algebra, and I've chosen one that is not maybe popular for people in class algebras, but I think it's good to illustrate the difference. And let's assume that the arrows A and B are both zero graded. So then this category is really the bounded derived category of the module category of this algebra, and the corresponding geometric model looks like this. So this is the surface dissection 1 and 2, And we had sort of an empty unmarked boundary component here. So we replace it by a mark point in the interior. So this is the dual ribbon graph. Okay, so 1 and 2 themselves are curves connecting white marked points. So they correspond to objects in the derived category. And indeed, gamma 1 corresponds with some grading F1 corresponds to some the projective P1 in some degree if P well, I don't know, or maybe just P1 in some degree M1. And then gamma 2 corresponds to the projective P2 in some degree M2. You could, for example, have this, here we have A, and here we have B, and you could have this curve, let's call it maybe delta. Okay, so delta is then a two-term complex. So delta with some grading G gives you a map from P2 to P1 induced by A, where this is in some degree, I don't know what I should call it, N, and then this should be in degree N +1, -1, yeah, depending on whether you go, it's homological grading or not. Okay. And then, yeah, what about maps? So we have P1 to P2 and P2 to P1 are two maps. And so we get P1, no, maybe let's do P2 to P1. So this is the map induced by the arrow A. And this is now a map, and this has now a mapping cone. And I said the mapping cone is the resolution of the crossing. And I guess the resolution of the crossing. Okay, so let me see. So we have here, so we go along, we start here, go along here, go along here. So this should be the, Südalo, is it P1 to P2 or P2 to P1? Okay, I think it should be this one, and then I do from 2 to the one induced by A. So it's P2 to P1. Okay, I think this one should then be the one that's going from also P2 to P1, but now as a complex. Okay. Yeah, so I didn't quite do what's in my notes, which is always a bad idea. Okay, in this example, we also have an infinite one. So we just circle around this and maybe call this epsilon, and then epsilon would be simply given by, you start by P2, then you have P1, then you have P2, then you have P1, and you just keep on going. And so this is A, B, A, B, and so on. Okay, so these are the objects in that category. Okay, and why? I mean, okay, so this is nice because, of course, derived categories are difficult to understand, but it turns out that this is also connected more generally to geometric objects by the work of Hayden-Katakov and Kontsevich. Okay, so first what they do is they characterize when these DG Genter algebras are homologically smooth. So A delta is homologically smooth if and only if. So what does homologically smooth mean? It means that A is perfect as a bimodule, or it has a finite projective bimodule resolution. If your algebra is zero graded, then this means the global dimension is finite of your algebra. Well, at least in the case of Genter algebras. And this is the case exactly if A delta has no oriented cycle. of, well, what I call, or generally people call, full relations. And what does that mean? That means that every subpath in that cycle is in the ideal. Okay, so for Genta algebra, what you don't have is something like this. Okay, so this is not homologically smooth. And then this algebra is proper, which means that the cohomology algebra is finite dimensional. And actually, if the algebra is concentrated in degree 0, it's the homology algebra itself, and that means it's finite dimensional. And of course, it's not finite dimensional if it has no oriented cycle with no relations. Okay, now that we know when such a Genta algebra is homologically smooth, why are we interested in that? That's because the derived category of homologically smooth and proper Genta algebras, graded Genta algebras, actually is known from geometry. Okay, so suppose that this is homologically smooth and proper, then this derived category with finite total cohomology is a triangle equivalent to the partially wrapped Fukaya category of the surface with the line field that is induced by the grading of the ribbon graph. So this is the partially wrapped Fukaya category of this surface with these marked points and the line field. Okay, and it's Haydn, Kotsakov, and Kontsevich actually showed this direction. So they start with this Fukaya category, and then they show that it's triangle equivalent to this derived category of a Genta algebra. And then Likili and Polichuk, they start with a graded Genta algebra, and then they show that they construct the surface and the line field, and they show that the derived category is equivalent then to that Fukaya category. Okay, so this is about the surfaces and the link to Genta algebras. So now let me tell you about cutting surfaces. So if you, yeah, so probably even if you don't know the Genta algebras, then sort of cutting surfaces is probably something that you have done before. Cut surfaces. Okay, so we have S delta, a graded surface dissection. And then we take gamma, an arc in here, so an edge of that surface dissection. Okay, so then we define the cut surface along gamma to be the surface S, how do I write it? S gamma, M gamma, delta gamma, obtained by cutting along gamma and then contracting. So obtained by cutting gamma and then contracting. Okay, and so let's look at this in an example. So here's our surface. Here's gamma going from some marked point P to some marked point Q. And there's a surface dissection somehow like this. Okay, and gamma is one of the arcs of the surface dissection. Okay, so now we cut. Well, this really cuts the surface into two. Oops. So also we get 2 points here. And okay, here we are. This is our cut surface. Of course, I should really also draw this dual graph. Okay. Okay, here we go. And then maybe let's not draw it here, but let's contract our cut edges. So then we get a disconnected surface. So we have this here. And here we simply get a triangle, and also is sort of works with our dual graph. Okay, so here's our cut surface. Okay, so this is where I wanted to make a link with the cluster theory, because in exactly this operation has been looked at. Yeah. Yes. 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 Exactly. I mean, if it's in a torus, you can, yeah, depending on your arc, yeah, you can introduce a new boundary. Okay. So the remark is, okay. So cuts appear in cluster theory, namely cuts of surface triangulations correspond to Calabi-Yau reduction of the corresponding cluster categories. And this was shown by Marsh, by Bethany Marsh and Jan Palu, in the case where all the marked points are on the boundary, and then by Zhou Yu and Zhou Yu in, I can't remember the date, 2017, when there are also marked points in the interior. Okay, so this is just an aside, because this is a cluster algebra program. So here's a link with that. I need to hurry up a little bit. Okay, so then we have a proposition with Wan Chang, Haibo Jin, where we show that the cut induces a unique grading or a unique line field. Well, okay, well, maybe not unique. I mean, unique for our purposes, I should say, on the surface in a really quite natural way. And furthermore, the other point is that S gamma, M gamma, and delta gamma is again a graded surface dissection of the good form, meaning that the polygons are of the two types that we want. Surface dissection associated to a gentle algebra. And let's call this gentle algebra a delta gamma. Okay, so now we want to cut not only at one edge, but at several. And for that, we need to convince ourselves that it doesn't matter in which order we cut. And we can do that by looking at the algebras and comparing those. And what do we have? So this is maybe a proposition 2, is that if we have gamma 1 and gamma 2, two arcs in delta, then the algebra where we first cut along gamma 1 and then cut along gamma 2 is isomorphic to the algebra where we first cut along gamma 2 and then cut along gamma 1. So that means if we now take a subset of delta, we can just cut one by one, and we get an associated algebra for the cut surface. Okay, so we got this cut surface dissection. Okay. Okay, so this is one side of the story. On the other hand, we have this cutting set. So on the other hand, gamma can be endowed also with an induced grading. And how do we do that? Well, it's very simple. We add the gradings up. Okay, so suppose in the original dissection we have I, J, and K, and then we have some arrow with a grading A and some arrow with a grading B. And suppose that I and K are in our set that we cut, but J is not. Well, then we basically in gamma, we only have I and K, and we get a new grading AB, such that the degree of AB is the degree of A plus the degree of B. Okay. And furthermore, the orientation of our original surface dissection gives an orientation of gamma. So gamma really is a ribbon graph. It's a graded ribbon graph. So it gives rise to its own surface. So gamma inherits an orientation from delta. So it is a graded ribbon graph or ribbon subgraph of delta. Maybe I should have said in other words. And so it has its own surface. So it generates a surface such that gamma is the deformation retract of that surface. Then we glue the mark points of that onto the boundary. So the vertices of our ribbon graph become the marked points. And well, this becomes the surface dissection. Okay. And so, of course, if we have the surface dissection by our first result, we know that we have an associated Genta algebra with that surface dissection here. Okay. Right now, I think I can state the main theorem because we have all the ingredients. Okay, so the two results. So the first one is okay, so we have our graded surface dissection. And some subset gamma of the dissection, then there is a recollement of DG Gentile algebras, well, of derived categories, sorry. Oh, 10, 12 algebras. You just, I mean, we get the graded Gentile algebra and then it has 0 differential. So this is important. So in the middle, we start with our dissection. We have the associated Gentile algebra to that surface dissection and then take its big derived category. Okay, well, okay, so it's a DG module, so it's the derived category there. Okay, then we have our cut, and so we get this cut dissection which sits in the cut surface. So here we're in the cut surface, and we have the associated Gentile algebra and take the derived category, and then we have a fully faithful functor here which has a left and right adjoint. So this is the left part of a recollement. And what is the right part of this recollement? So this data already tells us that there is a recollement. But the question is, what is the right part? And it turns out, well, here we simply take the cut, our cutting set, take the associated Gentile algebra, and then the derived category. So this is the recollement. So this is where gamma is the ribbon graph, the subgraph of delta, which is induced here. Okay, so this is the recollement. Furthermore, if all 3 algebras happen to be homologically smooth, if all 3 algebras are homologically smooth, then we get a corresponding recollement of the bounded derived categories. So these are the ones that are triangle equivalent to the partially wrapped Fukaya categories. So in some sense, we get a recollement of partially wrapped Fukaya categories here. Okay, so I think maybe an example again, before I state some sort of geometric result we can get by using algebra from this. Okay, so first let's do the example. So let's take as a quiver something simple. So A, B, C. So it's linear oriented type A with 2 relations. And then let's take as cutting set 2 and 3. So our algebra corresponds to this surface dissection 1, 2, 3, and 4. We have the arrows A, B, and C. And right now we cut, and we cut here and here. So we cut along here, and then we contract. So on this side, this gives us the delta gamma. Here we have delta, and we get just left with 4 and 1. And here we have a new arrow A, B, C, which then sits in degree. And this is this grading I only mentioned, but didn't define, -2. Then if you take the corresponding derived category, if I write the algebras in this way, you get this as the left side. And then on the right side, we consider only the subgraph by of the cutting set. So a cutting set is what I have drawn in green. And so what I get here is this here, and I have the arrow B, which is actually in degree B, just as it was before. So this is the part that corresponds to that. Okay, and right. So now the last result actually tells us that this surface here, which corresponds to the subgraph, is also obtained by cutting. And we use causal duality to show this. And we tried to first show it geometrically, but it was hard. And then we realized that we could simply use causal duality, and then it was very easy to show. And let me tell you how that surface on the right is obtained by cutting. So this is theorem 2. Okay, so the surface S of gamma, M of gamma, I don't know how I wrote it before. Okay, so this was very unfortunate because, of course, I use this notation for the cut surface and also for the surface generated by the ribbon graph. But really, okay, so here, I mean, the surface generated by this ribbon subgraph of delta. So the surface is obtained from the original surface by cutting along the arcs, which are in the dual graph, but not in the cutting set. And of course, in these examples I did, it's fairly obvious, but I don't know where the examples went. Oh, up here, it's fairly obvious that this is the case, but we're not sure how to show this in general. And let me maybe just finish with the example. So we had the surface here, which was the surface no, this is not the right surface, sorry. We had the surface we were considering before. Okay, so we considered the surface. Okay, and then we have the dual graph. And now we want to cut along this set here, which was not the cutting set. Remember, our cutting set was 2 and 3. So we take the ones in the dual. So now we cut along this edge and along this edge. And you can see that cutting along 1 star and 4 star. So this is 1 and this is 4. 1 star and 4 star gives us exactly the surface we want on the right side. So the right side of the recollement is also obtained by cutting. And yeah, this is what I wanted to say. Thank you very much for listening.
Thank you very much for the talk. And I will first ask participants in the room if they have questions.
Is anything known about non-oriented surfaces?
Non-oriented surfaces?
Like Möbius strip.
I have no idea, but it's a good question. Yeah, I don't know.
Thanks.
I mean, it can't be gentle. Well, maybe also gentle. I have no idea. But actually, no, I don't know. But yeah, I guess interesting question.
Hi, can you hear me? Oh,
yes, I can hear you well. Yes.
So there is a slight difference between the cutting processes in what you're doing and what Jan Palu and I did.
I see.
So
okay.
We didn't do the contracting step.
Oh, you didn't do the
I think
contracting.
we just cut and then left that as a boundary component on each side.
I see. Okay.
So do you have any idea why there's a difference there? What's going on?
Okay.
Or why do you need to contract?
Why do we need to contract? Because in some sense, so going from, as I said, from the left to the right, you have a homological epimorphism. So you get and it's sort of a quotient function. I don't know. I mean, I can't really. It just the models just fit that way.
I understand. Right.
I can't really say why.
For the categorical thing to work, you need to do that on the geometric
Exactly.
side.
In order for the categorical thing to work, it needs to be that way. And yeah, somehow.
Is there an idempotent in the?
Yeah, there is an idempotent, absolutely. Okay, so basically this. Okay, so what we do is we have this algebra here, and this algebra is actually yeah, we have an idempotent E, which is the sum for all I in gamma EI. And then we show that this algebra is quasi-isomorphic to some algebra, which now has a non-zero differential. So this is a true differential graded algebra. But for this algebra, then we can go to this quotient here, where we just simply, yeah, and then you kind of recognize the form of a recollement. And then we can show that this algebra here is also quasi-isomorphic to E, A, G, E, E. So now you sort of have this classical recollement, I guess. Yeah.
Very nice, thank you.
Any other questions from the room? I don't see any in the room. So are there any questions from the Zoom audience? You can unmute yourself or write in the chat. Well,
So I have a very naive question. This is Nathan.
Oh, hey, Nathan.
So is the case where your dissection is actually a triangulation, is that a silly case or is that an interesting case?
No, that's an interesting case. I mean, for example, when you have a triangulation, it just looks a little bit different because this is sort of the algebra that also appears in cluster theory. It looks a little bit different because it's not completely a triangulation because you don't have these marked points here, right? In this geometric model for the derived category, you only have 3 marked points, whereas in the model for the module category, which is the model coming from cluster theory, you would have 6 marked points.
can you repeat that again, Sibylle, because it didn't show up in the screen first.
Okay. So I'm saying that no, triangulations are very interesting indeed, except that the triangulations are not, I mean, what I suppose you think of triangulations, namely if you have an algebra with this quiver, then you would have an hexagon with an inscribed triangle. But in the model for the derived category, you have 2 gons here. So you only have 3 mark points as opposed to 6 mark points. But otherwise, well, I mean, they're not really triangulations, obviously. These pseudo triangulations are interesting as well. Does that answer your question, Nathan?
Yes, thank you.
Okay, great. Any other questions? I don't see any. Let's thank Sibylle for this nice talk again.
Thank you.